Good afternoon, and thank you for joining this briefing on Europe's first lightning imager instrument. My name's Gary Fowler, EUMETSAT's Instrument System Manager for the METEOSAT third generation program. With me here at EUMETSAT headquarters in Darmstadt, Germany, is our Director General, Phil Evans. And we're joined by the European Space Agency's Director of Earth Observation Programs, Simonetta Kelly, and Leonardo's Project Engineering Manager for the Lightning Imager, Guia Pastorini. Simonetta and Guia are joining us this afternoon from Leonardo's campus near Florence in Italy. For today's briefing, we will give a short introduction to the METEOSAT third generation program and the Lightning Imager instrument before presenting the first Lightning Imager animations. Our guests will then have the opportunity to provide their insights into the Lightning Imager and its uses. After our guests have had a chance to speak, we will have plenty of time for questions. Please enter your questions using the question and answer tool in Zoom. The METEOSAT third generation program is a collaboration between EUMETSAT and the European Space Agency. The first METEOSAT third generation imager satellite, or MTGI-1, was launched from French Guiana on the 13th of December last year and hosts the Lightning Imager. The MTG satellite is currently undergoing its commissioning phase. In other words, the instruments are being tested, calibrated, and their observations and data are being validated. The MTGI-1 is in geostationary orbit at 36,000 kilometers above the Earth, which gives it a constant view of Europe and Africa. The MTG system is the most complex geostationary weather satellite system built in Europe to date. And the Lightning Imager is the first instrument of its kind with a continuous view of Europe and Africa. You should have all by now had access to the media kit, which contains a series of animations produced from the very early phases of the Lightning Imager observations. The Lightning Imager has 4 separate cameras with 4 different but slightly overlapping fields of view. Each field of view looks at a diamond-shaped area on the Earth, and the animations are arranged to fit rectangular screens. So don't be too surprised if you see the land tilted by 45 degrees in the animations with respect to the usual map view of the Earth. The media kit contains animations from all 4 cameras over the complete field of view, as well as some animations zooming in on specific areas, such as Europe, Western Africa, and a part of South America. The animations we've produced are designed to show the importance of the Lightning Imager for the forecasting of storms. The type of data that we send to the meteorological services for weather forecasting purposes will be obtained at a higher sensitivity than the data we show today, and the process to remove any false readings. So the animations in the media kit contain preliminary raw data and aren't for operational use, but they give you a very good idea of the potential of this instrument. And now for the main event. The animation we're about to show is a compilation video featuring observations from 3 of the Lightning Imager's cameras. They show the lightning activity sped up so that 1 second of animation time corresponds to 1 hour of real measurements. For the zooms of particular areas of interest, the animation speed is slowed down to allow more time to see the developing lightning activity. I trust you'll find the animations as remarkable as I do. The animation was created using imagery captured by the Lightning Imager's north, east, and western cameras. Starting with the northerly camera's full field of view covering Europe and North Africa, you can see lightning becoming more active as the heat builds up during the day. A peak of activity is reached in the late afternoon and early evening as night falls. This is particularly evident in the Mediterranean, Spain, and Africa's intertropical convergence zone at the bottom left. We're now zooming more onto Europe, where you can see summer storms building up in Italy and the Balkans, but also in France, Germany, and Spain. Zooming in even further, you can see active storms in the UK. This demonstrates the lightning imager's capabilities even at higher latitudes. We now switch to the lightning imager's eastern camera, covering a large part of Africa. Central Africa is a recognized hotspot for lightning, and has one of the highest levels of lightning activity in the world. We zoom in now on the Sahel region of Africa. Here you can see the westward movement and evolution of a large cluster of thunderstorms. The animation shows how lightning is most frequent along the narrow, bow-shaped leading edge of the storm system, where the convection is most intense. Finally, from the lightning imager's western camera, we see lightning over Western Africa and the Atlantic Ocean. Lines of lightning can be seen moving from east to west along the intertropical convergence zone. Here the trade winds from the north and south meet and form storms that can intensify to hurricanes when they reach the Caribbean. Being able to detect lightning over oceans will be of particular benefit to aviation safety. I'm sure you agree that the lightning imager is showing very impressive results. Now I'd like to hand over to EUMETSAT's Director General, Phil Evans.
Thank you, and good afternoon, everyone. As Gary already said, I'm sure, like us, you found the images fantastic and curiously hypnotic as well. But of course, this isn't about nice images. This is about protecting lives, property, and livelihoods. Now, severe weather events take a very heavy toll on society. In Europe, they've caused 500 billion euros worth of damage over the last 40 years and have been responsible for the death of up to 150,000 people. These are huge impacts. Now, the EUMETSAT third generation satellite's primary role is to help forecasters and others to forecast severe weather events, to monitor them, and to mitigate their impacts on society. Now, as you'll appreciate, lightning has a direct impact on people. It can cause huge amounts of damage. You know, there are every year numerous fatalities because of lightning. But lightning also gives a very strong indication of where the most severe weather is occurring. Where there is the most severe rainfall, there is often lightning. And because of that, it will help people track and forecasting lightning. Now, this is already important, but in a world where climate change is increasing the intensity of severe weather events, instruments like this will become more and more important and will help weather services and weather forecast providers protect lives within Europe. So it's really a momentous moment and something that I hope will transform forecasting in Europe. And one other thing to say, as already been said, MTG is one of the most innovative weather satellites in the world, and this is the first lightning imager over Europe. And that's a huge success story. It's a European success story based on a partnership between EUMETSAT, ESA, and industry, who you will hear from. So I'm expecting this to be the start of a new era in satellite information over Europe. So thank you very much.
Thank you, Phil. Next, we have Simonetta Chiedi, the European Space Agency's Director of Earth Observation Programs.
Good afternoon, dear colleagues from the press, dear Phil and EUMETSAT colleagues, and also the colleagues from Leonardo. We are here in Leonardo, and I must say I'm particularly pleased to be here today in person because I've seen the lightning images before it was launched about a year and a half ago here at Leonardo premises, and today we are here to celebrate a real advancement in terms of technology with great results, initial results, of course, but fantastic results from this instrument. As Phil said, I think MTG, it's the third generation of what we have developed together. It's a success story of collaboration among European partners, between ESA, EUMETSAT, but also with industry. And I think it's very relevant to be here today with industry to show the results of the hard work that was carried out for over 10 years together. I have also here with me Pierre Coucou, who is the MTGI payload commissioning performance engineer who can support us if we have technical questions on the press side. Just to say, what is the role and the split of role between ESA and EUMETSAT on this third generation, which is the next generation of meteorology for the next 20 years? We plan to develop a system of 6 satellites overall. So MTGI is the first, the one launched in December 13 last year, is the first of 4 satellites that will be launched of this kind, and 2 sounding satellites on complement to that, which will guarantee about 20-30 years of meteorological improvement in terms of forecast. How? With resolution which is increased, with I would say everything that represents the next generation. So what we have worked with the industry together. EUMETSAT has designed all the requirements for the system, and that's the way we traditionally work hand in hand in our partnership relation. EUMETSAT is also in charge of this mission, but what we have done in the agency, we have designed a system which corresponds to the user requirements, a system that we have developed jointly with the industry, and a system that we have basically procured with the industry, also on behalf of EUMETSAT. So what we've been doing, we've been working with Thales in Cannes as prime contractor for this mission. We've been working with OHB, and this is typically, I would say, the expertise that ESA puts at the value of having various industries from different countries contributing to a project. And we've been working, of course, on the flexible confined imagery, which is one of the 2 main instruments on board the mission, with Thales, but also with Leonardo in Italy, here in Campi Bisenzio, where the lightning images that is, I would say, the hero today, is presented. And what we have achieved together, really something fantastic. You will hear all about it. Is a 4-camera with high-speed cameras on board. It covers about 84% of the Earth disk. It's improved meteorological forecast. It's now casting, and it's really something which has a very strong also economic value, not just in terms of contracts, but in terms of benefit for the citizens, as Phil said. And today at the European Union level, it's estimated that the value of this data is related to about 61 billion euros per year in the context of the European Union. So you understand the relevance, not just in terms of contribution to a strategic transport sector, but also contribution to climate change activities that will be done in the future. Basically, I would like here to thank Leonardo for the development they've done in terms of meeting the quality of the data that we now have seen initially. As Phil said, we will only finish the commissioning at the end of this year, but these initial images, these initial results already give us the feeling of the quality of the data, which really correspond to the requirements that were put on the table. I would also like to say that initially this mission was conceived many years ago. I still remember 2008 when we actually agreed on the subscription to this mission, and there was quite a fight among countries on who would put more on the table to contribute. We have managed at that time, together with EUMETSAT, to conceive a system that corresponds today with technological solution to those requirements. And then I'd like to say that we managed really to contain the situation in terms of schedule, but also meeting costs. And it was not easy in the last 2 years with COVID. And I think there everybody has performed at best. The project teams, the EUMETSAT teams, the industry teams, and I'd like to mention this here today at the occasion of this unveiling of the first results. Thanks a lot.
Thank you, Simonetta. Our final speaker for today is Guia Pastorini, Leonardo's project engineering manager for the Lightning Imager.
Yes, good afternoon, everybody. Yes, as already said, Lightning Imager is able to perform continuous lightning detection of the Earth in different kind of scenarios. So during night, in daylight condition, looking desert, but also look at the ocean with the sun reflecting into it. The instrument has 4 eyes, identical, with a slightly different orientation to cover more than 80% of the Earth disk. Its camera is able to detect even a single light event with a minimum dimension of 10 kilometers seen from geostationary orbit. That means like watching TV from 3 kilometers of distance. The minimum duration of a lighting pulse is 0.6 milliseconds. That means 1,000 faster than the blink of an eye. The specific wavelength selection of the lightning spectral feature, the oxygen triplet, is achieved through a narrow band filter, one for each camera, with just 1.6 nanometer of bandwidth in all operative conditions. The brain of the instrument is a powerful and high configurable electronic detection chain, free of bottleneck, able to cope with the worst not nominal in-flight scenario. A data regulation concept is implemented to manage a variable flux of data, achieving an average detection probability greater than 70%. Each camera can acquire 1,000 of images per second. This big amount of video data coming from each detector are analyzed on board and reduced by a factor 1,000 in order to provide to platform a constant flux of useful and already cleaned mission data. The body of the instrument is a thermomechanical structure in composite material, interfaced with satellite by 3 titanium bipods in quasi-isostatic mounting configuration. The heat coming from the board and the one coming from the sun are dissipated through a radiator faced to the cold space. Last but not least, the instrument is able to guarantee its performance for 8.5 years in geostationary environment. Thanks.
Thank you, Guia. Now we'll take questions. If you haven't already, please use Zoom's Q&A tool to ask your questions. Okay, our first question then is, where will all the data be stored? So I think I'll give this one to Phil.
Well, we have a data center here at EUMETSAT headquarters where we archive a lot of data, but we're also disseminating this data to operational weather services, and depends on their needs and requirements, they will archive the data as well.
Thank you, Phil. Now, the next one is, how exactly can the lightning be localized, and how is the quality of the observation compared with terrestrial sensors? So these are quite specialist. I think that maybe we can go to Jochen. Jochen, are you online?
Yes, I'm online, yes. I mean, because we are actually measuring on top of clouds, so we are, let's say, seeing scattered light that has gone through the clouds. I would say the localization is about a few kilometers in that sense, because it is not like a point source we are seeing here. The quality of observations, of course, we are still working on that to get the exact numbers, because that is part of our commissioning activities. But as a kind of a general rule, I can say that we expect our performance to be better on the cloud-to-cloud lightning, which is actually a very important part of the lightning process. So that is, let's say, the biggest, delta we have to the ground-based systems. But to get exact numbers, we have to wait to the end of commissioning.
And the next question is, so as a common EU citizen, how do I know something has changed? For example, in my weather app on my mobile phone. So I think, Phil, you're up again on this one, I'm afraid.
No, that's fine. I think what you'll see is, well, basically an improvement in forecasting for severe weather events. I know organizations specifically provide lightning alerts for users. Well, those will improve. But moreover, the forecast that you get, particularly short-term forecasting, and short-term forecasting is up to a few hours, those will really improve because of the observations of lightning strikes.
So the next question says, how can this improve aviation safety? So again, sorry, I'm picking on you a bit, Phil, but it's no,
it's fine. Well, I'm glad you raised the issue of aviation. I mean, a number of sectors are affected by lightning directly, but aviation is one of the principal ones. So lightning presents quite a risk to operations. An ability to track lightning, find its location, allows aircraft operators to route plan more efficiently and to operate in a more safe way. Now, one of the features of the lightning imager is its ability to monitor lightning over the oceans, which isn't easily done or done at all by other systems. And of course, in the Atlantic is an extremely busy air traffic route. So being able to track lightning over that region is really quite important.
okay. And how can you specify more how it will improve exactly weather forecasting? So I think we can hand across to the MTG mission scientist Jochen on this one as well. Jochen, if you're
all right, I'll make another attempt on this one. So we have been talking about this capability to improve our early warning capability, and that is because we do see the earliest part of the, let's say, severe weather form, which is the cloud-to-cloud lightning, which not really visible otherwise, except to this kind of sensors, and that is one of the key points. But in normal, regular work of a weather service, we have which we call the bench forecasters, who are looking at data constantly, and they're seeing if they have to give a warning or not for the audience, let's say for the public, and this definitely adds their confidence to actually issue these warnings or not issue these warnings. And that is the kind of a big added skill we get from this kind of data.
okay. Thank you, Jochen. So one directly to Phil this time, so I don't have to choose. Hi, Phil. Could you describe in more detail how lightning data will improve severe weather forecasting? Your quote in the press release says severe storms are often preceded by abrupt changes in lightning activity.
Well, I think this was partially covered by Jochen's answer just before. Being for short-term forecasting, you're able to see intense weather events developing and provide short-term warnings to the population about those severe weather events. But also, the development of intense weather is also associated with lightning. So lightning, basically, information on lightning allows you to understand and predict the movement of severe weather events.
Okay, so the next one we have is on data availability. When exactly is the data available to national weather services? And is there already feedback from these institutions? So
yeah, so the images we're showing you today are very early images, and we're going through a long process of commissioning, which will test, validate, calibrate these images, and we'll move towards a situation where the data can be provided operationally. That means that it can be provided reliably 24/7. That's incredibly important because if you're using this data to provide warnings and advice to a country, you need to know the data is there and available. So the likelihood is that commissioning period will finish towards the start of next year, and that's when we will make the data widely available operationally. In terms of feedback from weather services in Europe, I mean, there's a huge amount of interest in this instrument because it's innovative, because it's new, because we haven't had an instrument like this over Europe. They're very excited to see in what ways they can use this and in what ways they can enhance the services they provide to citizens.
And our next question is, will future satellites be better covering the northern areas like the Baltic and Scandinavia? I think maybe this one can go to Simonetta, if you're available for this one.
Yes, thank you. Basically, we have various weather systems. One is the Arctic weather constellation, which is currently in the making, which is a project of a new nature in the agency, in European Space Agency, that we are currently building, that we plan to launch end of next year, that will be complemented by a constellation of 20 satellites to be complementary covered by EUMETSAT. So again, a collaboration on meteorology, particularly devoted and dedicated to the Arctic region. And this is new. It's new not only for the way we work with the industries, for the much more agile mechanism of integration, of collaboration of industry. I went and saw in Sweden the Arctic weather satellites being finally finalized in terms of building a couple of weeks ago. We really look forward to launch it not too far from now and have the complementary constellation funded on the EUMETSAT side. Also, on top of that, if I speak with a European Space Agency hat, of course, I can say that there are lots and numerous Earth observation satellites which are devoted to the Arctic region, and which are not necessarily only MET satellites. And I think there are Crystal that we're currently building based on the Cryosat heritage. I think of Roselle, so many more Earth observation satellites that, of course, can complement data over that region, but are not just meteorological.
Thank you, Simonetta. Our next questioner then asks, will there be any warning systems associated with the lightning imager? And will a particular country receive specific alarms? So maybe if we can ask Jochen that one.
The EUMETSAT is only providing data, and our member states' Met services are then taking care of how to use the data. So they have their own ways of issuing warnings to the public and their own methods of actually analyzing the data and giving out these warnings eventually.
Okay, thank you very much, Jochen. The next question is, how much data is acquired and how much data is sent to the Earth in terms of megabits and megabytes per second? So I think this one can go to GUIA as the instrument manufacturer. Thank you.
Yes, okay, each detector, we have 4 detectors in the instrument. Each detector provides 48 gigabytes per second to the front-end electronics. And this onboard processing algorithm is able to reduce it up to 30 megabytes per second, which are transmitted to platform. So we have this onboard algorithm, which is able to, let me say, the instrument is able to recognize which kind of background is seeing, is looking, and it's able to adapt its threshold in order to maintain this constant flux of useful mission data.
Okay, thank you, GUIA. The next question is, the number of lightning strikes increases with climate change. How does the lightning imager help to find out more about these climate dynamics? Bill, do you want to take this one?
Yes, thank you. So as I mentioned previously, the most recent IPCC report identified that a whole range of severe weather events across the globe are increasing in frequency, whether that's drought or severe precipitation events. So that's something that's recognized in the climate predictions. Now at EUMETSAT, we already have long records of observations of the Earth going back more than 40 years. These are really important because they provide coverage of the globe, and that they're quite objective. They're from space, then they don't suffer from any issues of being on the ground, so they're very reliable. Now, what we hope is that over a period of time, the information we have about lightning data will show what sort of trends there are. And by understanding the trends in the atmosphere, that gives us some insight into the atmospheric dynamics. And along with lots of other information and observations, and along with climate modeling, it will give us a better handle on what's happening in the atmosphere with climate change.
Thank you, Phil. How are the groups of satellites, MTGI and MTGS, supposed to cooperate? There are differences, pros and cons. So again, I think this one's for you, Phil.
Well, as I think we touched on earlier, the full configuration of the MTG system is 3 satellites. So there are 2 imaging satellites. One takes images and lightning images over the full disk of the globe. The second imaging satellite, when launched, will focus on Europe and provide much more frequent updates of imagery from Europe. And then there's a third satellite, which is a sounder satellite. Now, we're used to seeing images of the Earth that are flat, 2-dimensional, if you like, but sounding satellites are capable of taking a profile through the depth of the atmosphere, which means over time they're able to provide a 3D picture of the atmosphere evolving over time. So they don't actively cooperate, but the instruments on these satellites have been designed to have the maximum synergy between them, so the whole system can benefit society to the greatest extent.
Thank you, Phil. The next question is, what is the difference of this system to the American? So this is the GLM system, in use in the GOES East-West already since many years. I think maybe we can put this one to Simonetta.
I'll pass the floor on this one to Pierre.
Yes, so the instrument on GOES is called the GLM, and it has the same working principle as the lightning imager. So it's also observing a surge of light into this 777 nanometer wavelength. But in terms of features, so the LI has a smaller pixel size, so with a better spatial resolution, with a larger coverage, because we cover Europe, Africa, also the Atlantic Ocean and a bit of Middle East, whereas the GOES is more centered on America. Yeah, the integration time is smaller, so we take acquisitions every millisecond, where the Americans are 2 milliseconds. And then in terms of data, we download a bit more data. We download the data of the landing itself, and also its neighboring. So, and we also have a bit more algorithm to process data on board to allow us to have optimized bandwidth.
And if I may compliment to Pierre, just to say that there is quite a ratio in terms of overall investments. I must say here, Europe is pretty efficient in terms of budgetary investment associated to these missions if we compare the European and the American ones.
Okay, thank you, Simonetta and Pierre. Is the observation of lightning via terrestrial sensor systems and warning systems now obsolete? And I think, again, Phil, this is one for you.
Well, the short answer is no. I mean, there are a number of different sorts of terrestrial observing systems, and they have different features. Some of them are quite limited in geographical coverage. Others have very wide geographical coverage, but the number of lightning strikes that can be picked up is potentially quite small. The lightning imager is special in that it can pick up cloud to ground and cloud to ground strikes, and it can also monitor lightning over the oceans, which terrestrial systems generally don't do. So actually, these data sets are very complementary, and I know some of the institutions in Europe are quite specifically excited about how these data sets can be combined to find new applications and provide new services.
Okay. Simonetta mentioned investment. What is the overall cost of MTG and the MTGI-1 satellite? So this is directed to you, Simonetta.
Right. Yes, thank you. I can comment that the ESA investment by member states has been 1.4 billion for the ESA contribution, and I let Phil comment on the complementary EUMETSAT one.
So the EUMETSAT funding for this is about 2.9 billion.
And this covers overall also not just the investment in the development of the satellite, the launching, but also the operations for about 20 years. The total investment costs between ESA and EUMETSAT.
Thank you very much. I think we've now run out of questions. So thank you very much for your questions. And so, okay, that wraps up today's proceedings. I'd like to thank our speakers and thank you very much for joining us today. We hope today to have given you a good appreciation of the exciting new instrument capabilities and the benefits that it will present for the future of weather forecasting. Please don't hesitate to contact the EUMETSAT or ESA press offices for more information. Oh, there's another question come through. Can the system detect other phenomena, not only lightning, like bright flashes of any origin, understanding that they have to be very energetic, but still? And this is one for Phil.
So the system is designed to detect lightning. It's optimized for that. And of course, we'll be providing lightning information products through a lot of processing, and that processing will cut out any extraneous information. So really what will come out of this is just information on lightning.